All right, here we go with our first notes on logarithmic functions. So today we're going to be talking about evaluating logs. We're going to be rewriting logs and exponentials. We're going to be talking a little bit about inverses. If you're following along with me, this is pages 10 and 11 in your notes packet. To start, I want to start off with this little warm up here. Let's go ahead and evaluate each of these exponents. So number one, 3 to the first power is just 3 by itself, 3. Next up, we have 3 squared, or 3 times itself 2 times, 9. And now I want to solve this equation. 3 to what power gives me 27, or 3 to the third power gives us 27. So 3 cubed, 3 times 3 times 3. For number 4, we have 3 to the something equals its reciprocal, 1/3. Well, the exponent that gives us the reciprocal is the negative first power. So 3 to the negative 1 is 1/3. Let's go ahead and graph this exponential function, f of x equals 3 to the x. We're going to do that by constructing a table of values. So I'm going to make a table of values, x, f of x, and I'm going to choose values, x values between -2 and 2. So evaluating the function, f of -2, we have 3 to the -2 is the reciprocal of 3 squared, or 1/9. 3 to the -1 is 1/3. 3 to the 0, or anything to the 0 power, is 1. 3 to the first, or just 3 to the 1, is itself 3. And then 3 squared is 9. Go ahead and plot these points. So we have -2 comma 1/9. You can kind of approximate. We have -1, 1/3. Again, kind of approximate there. 0 comma 1, that's our y-intercept. 1 comma 3. And 2 comma 9. Now remember, this is the parent function, 3 to the x. We're going to have a horizontal asymptote at y equals 0. So go ahead and draw that in, that horizontal asymptote, as a dotted line, and sketch in your curve. Don't forget those arrowheads on each end, and as you're approaching your asymptote, try to get as close as you can to the x-axis without crossing. Okay. Now I want to graph the inverse of f of x here. And we're going to construct a table of values. So in order to do that, I'm going to use a different color here. If you remember, a table of values for the inverse of f is where all of the inputs and outputs are flipped. So then if we're constructing a table of values, all of our outputs would now be inputs. So we would be going from 1/9 to 1/3 to 1 to 3 and to 9. And the inverse, the outputs would be the inputs from the original. So we have -2, -1, 0, 1, and 2. Now go ahead and plot these points. So 1/9 comma -2. We go to the right 1/9, again, just approximate, and we go down 2. We have 1/3 comma -1. We have our x-intercept, 1 comma 0. We have 3 comma 1 and 9 comma 2. Now you might notice that if you remember about inverses, the inverse to a function is graphically that function reflected over the line y equals x. And you might see that here. If we were to just imagine, and I'll draw this in a different color. If you imagine the line y equals x, it's reflected over that line there. So here we have our inverse. And you might also notice that instead of a horizontal asymptote, our inverse has a vertical asymptote, x equals 0, where the function gets really, really close to the y-axis but never crosses. So let's take a look at exactly what that inverse is. So this new notation for our inverse functions for exponentials is logarithmic functions. Logarithmic functions are the inverse of exponential functions, and we write them as such. Log base 3 of 9 equals 2. And essentially what this means is we're saying that the input x is 9 and the output y, or f of x, is 2. And so if you visualize these as you would exponentials, this is similar to saying 3 squared equals 9. Over here, again, our input is 27, our output is 3. We would be saying 3 cubed is 27. So if it's helpful for you to think about these logs as rewritten exponentials, by all means. Lastly, we have 3 to the negative 1 is 1/3. But notice that our input, again, is the argument of the log, 1/3, and the output is -1. So what about this one here, log base 3 of 81? And I want to evaluate this here. So this is essentially saying 3 to the something, what power, gives us 81. So take a moment, think about that. What power do we raise 3 to get to 81? The answer to that, 3 to the fourth power, is 81. Now, if I wanted to rewrite number 6 as an equation here, as a function, f inverse of x, then we would be saying instead of 3 to the x, we're saying that this is now log base 3 of x, and we're flipping around these inputs and outputs. So now the input of our original function is now the output of our inverse, and likewise the output of our original function is the input of our inverse. Let's go ahead and determine whether or not these logs are true or false. Again, as a reminder, log base b of y is read just like that, log base b of y. So where y is the argument, it's the input of the log. So now I want to determine whether these are true or false. Again, you can think of these like exponentials. So 2 to the 6th power equals 64. If I were to write that out, 2 to the 6th power equals 64, and I have to determine whether or not that's true. Well, is 2 to the 6th power 64? Indeed it is. This is true. For letter B, we have log base 2 of 8, or what power do I raise 2 to get 8? And the answer to that is 3, not 4. So this is false. So this would have to be 3. We're saying what power do I raise the base to in order to get the argument 8? Lastly, log base 7 of 1 equals 0. Well, we have what power do we raise 7 to get to 1? And that answer is 0. Anything to the 0 power is 1, so this is true. All right, let's go ahead and rewrite some of these exponentials as logs. So this would be our base of our exponential is our base to our log. So log base 15. The argument of the log is what the exponential evaluates to, so 225. So log base 15 of 225 is equal to 2. Or in other words, what power do we raise 15 to get to 225? The answer is 2. Next up, we have log base 2. Again, the base is still the same, of 16 is equal to 2. Is equal to x, sorry. It is equal to x. There we go. So 2 to the x equals 16. And next up, this is the general form for a log. We have log base b of y is equal to x. So what power do we raise b to get to y? And that would be, in this case, x. All right. There's a couple special logs that we talk about, special bases in particular. The first is the common log, or the common logarithm. And the common log is log base 10 of x. So if you have base 10, we just assume that it's the common log, and we denote that as just log of x. So the log with no base written is referred to as the common log, or log base 10. Likewise, the natural logarithm is log base e of x. And that is written as ln of x, or the natural log of x. And that's assumed to be the base e. log base e. Let's go ahead and evaluate some of these logs. So example 3, letter A, log base 4 of 64. We're saying what power do we raise 4 to get 64? And the answer for that is 3. We must cube 4 to get to 64. Next up, what power do we raise 81 to get to 9? Well, 9 is the square root of 81, so therefore we must raise 81 to the 1/2 power to get to 9. So log base 81 of 9 is 1/2. Log base 1/2 of 32, what power do we raise 1/2 to get to 32? Well, I know 2 to the 5th is 32, but 1/2, in order to take the reciprocal and get 2, we would have to make it negative. So log base 1/2 of 32 is -5. Letter D, log of 100. Again, there's no log base written here, so we can assume that it's the common log, or log base 10. So what power do we raise 10 to get to 100? The answer is 2. Letter E, what power do we raise 3 to get 1/27th? Well, you might notice this is a fraction. We're taking the reciprocal, and we're also cubing 3 to get to 27. So therefore, log base 3 of 1/27 is -3. Last up, we have ln of e, or the natural log of e. Now remember, the base of the natural log is e, so what power do we have to raise e to get e? Well, that's just 1. And the natural log of e is 1. All right, we got 2 more examples for today. So here, example 4, given f of x, find the inverse. So as a reminder, you can always find the inverse algebraically by switching the input and output and then solving for that output. Or in other words, if we were to represent this as y equals 2 to the x plus 3, what we can do to find the inverse is switch x and y and then solve for y. So let's go ahead and do that. So rewriting the equation, x equals 2 to the y plus 3. We can solve for y by first subtracting 3. So we have x minus 3 equals 2 to the y. And then in order to get y by itself, let's rewrite this as a log. So this is saying log base 2 of x minus 3 equals y. So log base 2 of x minus 3, and don't forget those parentheses. That entire x minus 3 is the argument of the log, equals y. And then finally writing as an inverse, f inverse of x is, again, log base 2 of x minus 3. One more example for today. Now I give you a log and I say find the inverse. So you can expect that your answer is going to be an exponential function, knowing that the inverse to a log is the exponential and vice versa. So again, we can rewrite this as y equals the natural log ln of x minus 5. Switching x and y, we have x equals the natural log of y minus 5. Now, in order to get rid of that natural log, we can rewrite this as an exponential. So log base e to the x is equal to the argument y minus 5. So log base e to the x, e to the x is equal to the argument y minus 5. And then solving for y, add 5 to both sides, y equals e to the x plus 5. So then the inverse, f inverse of x, is equal to e to the x plus 5. And that's your answer. All right, so we're going to get a whole lot of practice on evaluating logs, rewriting logs, finding inverses. We'll see you tomorrow in class. Have a great day, everybody.